Hello everyone, welcome to the lecture. Today we want to wrap up our introduction to Spark. It will be a combination of the slides and live demos like before. All right, and this will be the last lecture. You have a special lecture starting next week. It goes back to normal, okay, and you will attend the lecture at 10 o'clock. The plan is to start with these new slides and I show some demos, and then at the end of the lecture I will cover the remaining slides we had from last lecture. All right. The example I want to present today is a movie rating, and I use this example to introduce more advanced features in Spark and to have a better understanding of the performance of Spark. Again, as we said before, this course is not meant to be a teaching big data frameworks like a Spark and Hadoop, but we taught you enough to get us started so that we can work on your assignments. And starting from the next session, we will mainly focus on algorithm design, and we will not introduce frameworks that much anymore. So that's the plan. So let's get started. So let me actually present to you the file that we have for this example, and I tell you exactly what we want to do. So I go back to my notebook. I will increase the font size here for you guys to make sure you can see better. So I've already installed and imported stuff for Spark, so it's ready to go. So I've downloaded two files. So this is my main file, rating.csv. So it's a comma separated file. I'm going to present different approaches. Some approaches are so slow that it takes forever to process this file. So I've also created this a smaller file here. All right. Actually, I can show to you if ls-h, sorry. Oh, I meant to add L as well. So I take an ls here. You can see that I have these two files. So the actual file is around 700 megabytes actually. And the small downsampled version is only 2 megabytes, 3 megabytes. Okay, so I use this in some of the slower approaches, and hopefully by the end of the lecture, I provide an example where we can actually process the original file as well. How does the file look like? So we can actually load it to Spark and start processing. Please let me know anytime you have any questions. Sorry. So we're going to load the file. So the file is in my local, a local directory. So I can load it directly, small.csv. And then here, what I can do, I can simply do like something like take 10 just to see what I have got in that file. Okay. All right. So this is what I have in the file. So the first row is the labels for the columns that we have here, and then we have the actual data. So in every row, we have user ID, we have movie ID, 31, for example. We have rating and timestamp that we don't care. We don't care about this last big number. Okay. So what does this mean? It means that user 1 rated movie 31 2.5. User 1 rated movie 1029 3. And there are other users too. We don't see all of them. If we take more, we'll see them. Okay. So we have a bunch of users rating a bunch of movies, and we have these ratings. All right. What do we want to do today? We want to calculate the average movie rating. So for every movie like this, 1061, I want to calculate what is its average rating. So many users have rated this movie. So one user rated it 1, one user rated it 3, like here, another user rated it 5. So we want to calculate the average. So at the end of the day, what I want to produce is basically a list of movies, like movie IDs, I mean, and in front of each movie ID, I want to present the average movie rating. Is that clear? Questions about what we want to do about this file? Everyone's happy? Okay. Let me know if you have any questions. There are only 8 of you here today, so don't be shy. All right. So let's see. First things first. Right now, every element in this RDD is a row of text, right? So I need to get access to the elements of that line. So it's a CSV file, so we have comma separated format. So I need to extract basically the movie ID and rating out of it. So the first thing we need to do is to tokenize it, because right now the whole thing is just one string, right? Every line is a string. So, but even before we do that, there's another issue. As you saw, the first line is the header of the file, right? So it doesn't contain actual data. So if I just implement something, that line messes up my calculations, right? Because it expects a number there and then there's a text there, which is the header, like the user ID, movie rating, something like that. So let's delete the first line. How can we delete the first line? Here's a trick, okay? That's one, but it works fine. So first, basically returns the first element of the RDD, which is the header file, the header line, right? So I store that in header variable there. And then what I will do, I do a trick like this. I will I'll do something like this. Data is, I'm reusing it because I don't need the original one anymore. So I'm going to do a map and say, hey, for every line, oh, sorry, a filter, okay? Only keep those lines that don't match the header. Make sense? So this way we can get rid of it. So keep it if it's different than header. Make sense? If I run it, and then it hasn't done anything because we don't have an action, so .take. We'll take 10, for instance. Now you can see that it's the same data, except that the first row is gone, right? You've got a question here. Are there native methods to directly read CSV? Yes. In addition to RDDs, Spark has a data frame concept, and there I believe that there are ways to populate the data frame directly from a CSV file. It does it automatically for you. All right, so this is it. All we have done is that we have deleted the first line. Got a follow-up question. Wouldn't it be simpler to just exclude the first line? I mean, I deleted from the file. I want to keep it because it's nice, because if somebody looks at the file, it's they can understand what we have in that file.
Professor, I was saying that instead of filtering and going row by row, right? So for data.filter, if we just excluded the first line from data here. So my understanding is that this lambda functions apply to every single row.
Yeah, so how should we exclude the first line?
I'm not sure how to do it in.
Yeah, so there is no clean way of doing this. So this is one way, and there are some other ways that are a bit more efficient, not that much. Yeah, it's not very straightforward. So basically, when you do something, it is applied on all lines, right? So that's the issue. But again, there are things like map partition that you can do a little bit more efficient way of doing this instead of like reading every line. A little bit more efficient, but none of them were really clean, like the way that you like to exclude it. So this is how we exclude it, basically. So now that we got rid of the first line, now we can start processing. So the first thing we do here is simple. It's like before. We can simply tokenize it, and we know this map, right? And we say lambda x for every line, tokenize it, right? We had x.split, and here, because it's a comma separated file, right? The delimiter is comma, right? And if I do take 10 on this, you'll see it's exactly the same, except that now I have tokenized them, right? Now they are part of a list here, right? We have produced like a list of lists, right? So for every line, now we have a list of values, right? They're still a string, but we have separated them into individual substrings, right? Now, we can do another level of cleanup, and that is, let's think about what we want to do. We want to basically, for every movie like this, we want to calculate the average rating, right? So all we need to keep here is the ID of movies and the ratings they got, right? We don't care about who rated what movie. We don't care, right? And we don't care about the timestamp at all. So let's get rid of them right away. How? Simple. So we say for every item that we have, which is basically this thing, right? For instance, so lambda, for every line like that, or every element, now I better say call it an element, right? Because we don't have a line anymore. So for every element, which is that list of items, what I want to produce instead of every item is a key value pair, let's say, right? Where the key is the second column. I want the movie ID. And the value is the rating for that movie. Make sense? If I do this, let's see what we get. So basically, we are going to replace this list with a key value pair, where this is the key, this is the value, and do the same thing for all of these lists, right? There you go. So all I've done is that I got rid of unwanted data, basically, and formatted my data properly so that I can implement my averaging mechanism, right? All right. So what is next? And let me know if you have any questions. Now, let me check my notes here, make sure everything is fine. All right. Now, here's a catch. So here, so what is the data type of x1 and x2? So when you look at this, what is the data type of this? Is it a number or it's a string, like text? It looks like it's a string, right? Because it's in quotes, right? So the issue is that later on, I want to perform mathematical operations on these numbers, right? I want to calculate the average. So I'm going to add them up. We are going to divide them by the count to calculate the average, right? But these are a string. Python cannot add two strings, right? They can add the strings, but it won't do what we want, right? It cannot do the mathematical operations. So so here we need to convert the second one, which is the rating, to a number, okay? And we can do that in Python by passing it to the float function. Float because it's a float, right? Because we have like 0.5, right? Things like that. Otherwise, it could be integer. So that's all I did. So now you can see that the single quotes are gone. Now Python considers the second or the value of this key value pair to be a number. Okay, makes sense? So, yes, I'll send you the notebook. So, so this is what we have. So this looks good. Now what we want to do is that, okay, this is a long list, and for example, for this movie, like 1129, it appears many times on this list, right? And every time with a different rating. So I want to bring this data together so that I'm able to perform the average operation. So a natural way of doing that is by using the group by key operation, right? So this is the key. I want to group all of its values so that I have this key and a list of all of its values, because then I can convert that list to the average of those values. Makes sense? So what I want to do is here, I want to perform aggregate by key on this data. All right. Sorry, I meant group by key. Sorry, aggregate by key actually exists, so don't confuse it. I'm sorry about that. So it's actually group by key. Okay, we want to perform group by key. So, and I think I should store this somewhere, right? Because this requires shuffling and it will take time. So I'm going to store it in aggregate results, for example, right? So it's the same data, except that we are going to perform group by key. So I run it and it returns immediately. And you guys know now that it is lying to us. It hasn't done anything yet, right? Because we don't have any action, right? I removed take 10, so there's no action. So if you really want to see what happened, we can do dot take on this thing. What happens? As you can see, it needs to think a little bit, okay? Okay, and there's also another issue, not an issue, but a presentation issue. What's the problem? It says, okay, I have that movie 1129, and I've prepared a list that contains all of your values, but it doesn't show us here, right? So I can convert that to a list so that it displays nice, but for now, trust me, it now what it produces is a list of basically values that were associated to this movie ID. All right. Now, what I need to do is I want to produce something like this, except that instead of this list, I want the average of those numbers. So a single number instead of this list. Okay. So how can I do that? Using a map, right? It's very easy. So it says every item that you have, I want to produce a new key value pair, right? Where the first element or the key of the key value pair is the same key. The movie ID is fine. I don't need to do any further processing on that. That's already fine. Now I have a list, right? So x1 is a list, right? List of numbers. I want to calculate the average of the numbers in that list. It's very simple. Python has built-in functions like sum that calculate the sum of numbers in a list. And then we need to divide that by the number of items in that list. So we can also use len now that returns how many things we have in that list. And that would be something like this. Sum of values on list x1, number of items on list x1. This will be the average of the numbers on that list, right? Now if I do take 10, bingo, this is what we wanted, right? Now we have 1129, this movie, the average rating is 3.3. Another movie at 1293, the average is 3.9, so on and so forth. This contains the information for all of the movies and not just this one. We are done, basically. The first approach. I'm going to implement it using a different approach next, but this was the first one. Any questions about what we have done here? Okay, so I have some slides that kind of explain these things again, and then I make a point at the end and I will present the second approach. So in this movie example, we started from an RDD, right? By reading the file, we know that every RDD has multiple partitions, right? Where we actually store the data. And we know that every partition can be on a separate physical server, right? In this case, in the example that I'm showing here, this RDD contains 3 partitions. So we can assume that the first one is on one machine, the second one on another server, third one on another server, right? Let's see what we have done. This is like the data that we had, right? The user, movie ID, and then the actual rating, right? So what did we do? We applied map, right? We applied that to split, and we basically converted that string into a list, right? So we tokenized, and then we applied another map, which basically extract what we really care about, which was movie ID and its rating, right? So we ended up with something like this. In both of these operations, you can see that things are embarrassingly parallel, right? Meaning that server 1 can take this partition of this RDD and apply this map on it and produce a new partition that belongs to a new RDD, and you can keep track of that. And then on this new RDD, server 1 can again, independently from other servers, apply the second map and generate this new partition, right? So I have 3 servers, each has a partition. Because they can do these things completely in parallel, they don't need to talk to one another, right? They can do these operations locally, right? And create new partitions, and we keep track of them and say, okay, this is a new partition. This is a new RDD with these 3 partitions, a new RDD with these 3 partitions, right? So everything's fine. No need to talk to one another, right? But when we perform group by key, you will soon realize that we can no longer perform these operations independently from other servers, and I need to access to the data that live on other servers. How? For example, suppose that this machine is keeping track of movie 100. So this movie 100 has some ratings in this partition, right? It has some data in this partition and a lot of data in this partition. So sure, I can get some of the data because this is the same machine, right? Same machine. Okay, I have some of the data, so I add 4 and 5 to my aggregated list, right? And then, but I also need access to this 3. So this guy needs to send me 3, right? And this guy needs to send me 2, 4, 5, right? And I add that to my list, right? So on and so forth for other movies. So you can see that we need to talk to one another. This is a shuffle, right? It requires a Spark shuffle, which is slow. You realize that when I ran it, it took a few seconds to finish, right? And remember that I'm running it on the downsampled file that is only 2 megabytes. The original file is around 700 megabytes. And if I do that, it takes very long. And that's why I did not try it. Okay, so I didn't test it, but remember, if I perform group by on the original file, it's going to take minutes, okay, to finish. So, and then finally we did another map, right, to take the average of those numbers, and that's what we found. Now, the question is, we talked about the concept that can potentially combine the data and actually decreases the amount of data we need to shuffle, right? Can we do something like that here? Does the Spark have combiners? Well, not explicitly like Hadoop, but there are other operations that we can use instead of group by key that implicitly use combiners. Group by key does not use combiners, and because it has no opportunity to combine, because there's no way to aggregate the values, right? You have to actually keep the values, right? So I have 4, I have to copy 4, 5, copy 5, right? We are not aggregating, for example, we are not adding them up, we are not taking the average yet, right? So we cannot shrink the amount of data that we have. But there are other ways that can do that, like reduce by key, correctly mentioned by Yasin, right? So how can we run, how can we do this using reduce by key? So it will be a little bit more tricky. I'm gonna copy this over to a new block, okay? This time, I'm actually going to use the actual file because this new technique is actually faster and it can calculate this over the original file. So let's use the original file now. We are done with that one. So I reuse that variable. I run it. Everything is fine. Now let's redo this, and I will cheat a little bit, because the tokenization part is pretty much the same, right? And also let me copy this part. Again, we have data file, we apply map, we tokenize, and then now here we have a problem that I will talk about in a second. And then after that, we want to do reduce by key. There's an issue. If you run this, it won't run. First of all, we're not done. Reduce by key needs a function, right? Because it needs to know how we should combine the values, because what happens is that reduce by key works on key value pairs, right? When you have 2 key value pairs that have the same key, it basically reduces those key value pairs into one key value pair where the key is the same key and the value is the value is what you define here, right? Previously in word count, we said add up the values, right? Because we wanted to perform count. But here we want to perform average, right? So what should I write here? So my data is key value pair, the key is movie ID, the value is the movie rating, right? And what we want to do, we want to reduce by key. So if we have like 100 entries for this particular movie, we want to basically compute the average of those values. So how can I reduce? Exactly. So as suggested here, actually what you're suggesting is that it is not possible to implement the average directly, right? The reason is the same as why you cannot use the reducer as combiner when we were using average, right? Because the way reduce by key works is that it basically, let me explain some, right? Like in word count that we implemented last time. So when you add up the values, right? It's very simple operation. So I have a list of numbers and I want to add them up. So I take the first number and I take the second number, I add them up, and then I take the result and I add it to the third element, right? And I take the result and I add it to the fourth element, right? Until I add up all of the numbers on that list. Makes sense? This is how reduce by key works when you add up numbers. But here I want to calculate the average. Can I take the first 2 numbers and take the average and then compute the average of the result with this third number and then calculate the average of the result with the fourth number? No, it is mathematically wrong, right? So we cannot do that. Average doesn't have that property, right? So for that reason, there's no way to implement something here that calculates the average of those numbers. So we need to use a trick, okay? And as suggested, we are going to basically convert this. So this won't work. I need to keep track of sum. So what I can do here, I can implement sum. So what happens is that we end up with movie IDs, right? And sum of their ratings, right? If I implement sum. So if I implement something like this, lambda x, sorry, it will be, I think, x and y, right? For two numbers, you do this to those two numbers, add them up, right? But this won't work. Why? Or it doesn't have enough data, right? Can you tell me what the issue is? Yes, I need some. The issue is that if I do this, it's fine. It produces some output, right? The issue is that I get a number, like for movie 100, here's the sum of the ratings. How can I calculate average? I needed to know how many numbers you added up so that I can divide this sum by that value to calculate the average, but you don't give me this number. So as suggested here, we need to keep track of how many numbers we are adding up. So here, yes, it's fine. Yeah, it's fine. So we add up the numbers, but you also need to tell me another piece of information, and that is how many numbers you have added up, right? So for that reason, I modify this data structure so that in addition to the rating, it also keeps track of count, like how many times we have added up these numbers. So I'm going to convert this into another key value pair, okay, where the key is the rating and the value is number 1. Okay. What do I want? So I need to change my ReduceByKey, right? Because right now it says, oops, I cannot add up to key value pairs. What do you mean? You add sum or add up to key value pairs, right? So we have to tell it what to do. So so we have to modify this, okay? Let me have a look at my note to make sure that I'm not missing anything here. Okay, everything's fine. So now we need to figure out how to change this lambda definition. So the meaning of x and y changes. Previously, x and y were two numbers that we were adding, right? But now x and y are like this. They're key value pair, right? So what we want to do, we want to add up. So what we want to do is we want to add up the first elements and then to keep track of sum like before. And then we also want to add up these ones to keep track of how many numbers we are adding up. Okay, so we are saying that we are going to produce a key value pair. And don't confuse two things. Don't confuse this key, which is the movie ID. I'm done with that, okay? This is automatically carried forward for me in ReduceByKey, right? I'm talking about this value here, which is a key value pair of its own, okay? When I talk about key value, I'm talking about this thing, okay? So we are adding multiple items that look like this. How can we add them up? So we need to add up the first items and the second items, okay? How? So x is referring to something like this, right? So it will be something like, what does this mean? x0. What does it mean? It means that, for example, if you give me, let me provide you some examples. So I'm adding up things like this. For example, rating, and number 1, right? And I'm going to add that to, like, for example, another rating, which is 4 and 1, right? So what I want is a new key value pair where here I add up the first element, so I want to produce 7.5, and I want to add up the ones, so I want to produce 2. right? So I'm trying to basically implement this thing. All right. So correct. So this is rating, right? X0 is the rating. What should I add it to? I should add it to the second element, so which is Y0, right? So in this example, this is X0, this is Y0. So this is X, right? This is Y. So this is X0, this is Y0. I want to add them up and they will constitute the key for me. And then for the value, I want to add up this and this. This is X1 and this is Y1, right? What did I do? Y1 should be it. Okay. I remove these things. Is there any question? I will stop here. Make sure everybody is on board. So at the beginning, we were adding up two numbers, but that was not enough, right? Because that would just keep track of sum. We needed to keep track of count as well. So we created, like we keep track of two numbers instead of just one number, right? And here, you don't have to use like key value. You can, for example, change that to a list, right? The data structure really doesn't matter here. It doesn't change that much. We don't care. So, but we, instead of a single number, we have a data structure that has two numbers, right? One is rating, one is count. And all we need to do in ReduceByKey, we have to tell it how to basically add up, because in Python, we cannot just add up those things, right? It makes no sense. So we have to give it our own definition of adding such a thing. So, and we did. Can we use sum instead of writing x plus 1? I think so. But remember that this is really adding up two numbers, right? Not a list of numbers. So what happens is that in ReduceByKey, we have actually more than two, right? We have many more, right? So for a given movie, we have somebody hated the movie, so it gave it 1, right? And then another person really loved the movie, gave it 1, it's 5. So we have all of this. So the way this definition works, it starts from the beginning, right, and applies that formula and moves forward, right? So it applies the formula in these two, calculates the sum, and then takes the result and adds it to this, and takes the results and adds it to this. This is how it works, right? So it's really adding two numbers, right? That's why we have x plus y. But sum works, I think. So that's the idea here. So let me get rid of, not get rid of that, get rid of this. And then at the end, I'm going to access this a few times. So let me cache it and run it. And it immediately says, yep, it's done. It's lying. It didn't do anything. So let's just do take. Oh, we have to take 10. Tell me what we have here. What do we expect? Movie ID, and then another key value pair, which is the sum of ratings and count of ratings. Let's see if we got it. This will take some time. You may say, this was supposed to be faster. Why is it slower? No, I'm running it on the 700 megabyte file. I ran the first one on the 2 megabyte file.
Professor, I have a
Yes,
question.
sure.
So if this is one RDD, right, then we have multiple cores available to use for this one RDD, right?
Sorry, say the first part again.
I'm saying that if this is a single RDD on a machine, let's say, when we have, let's say, 5 cores, right?
Right.
Then instead of going for the ReduceByKey going one element after the other, why can't we just split it into, let's say, 10 pieces and then do each of those sums operations on separately and then add them together.
So that's the idea, really, right? So the idea is that, okay, we have a lot of data. We are dividing it, as you're suggesting, into partitions, right?
Right.
Remember that at the end of the day, the goal is to implement this on a cluster that has multiple machines, right? So we divide it up. Every machine will be in charge of a partition or a collection of partitions. And they will do all of these things in parallel, right? So let me actually go back to my slides. And while this is running, let me actually explain what's happening here. So we wanted to make this faster, right? By trying to have a little bit of combining. So let's provide another example. Suppose that we only have two movies, 100 and 200, and we want to figure out how reduce by key is different. So reduce by key knows actually the operation that we are going to do, right? So these three partitions are on three different machines, okay? Before we send out the data for shuffle, we can apply reduce by key locally on every machine, independent of others. For example, this machine, right, doesn't know anything about other machines. It says, okay, look, I have 100, I have 100, and I know that you are going to perform reduce by key at the end of the day, right? So I'm going to perform reduce by key locally on here and say that, okay, so 100, so the key is the same. And then, sorry, the only thing that's different here, I use key value notation, but here I'm just using like regular column. So in my implementation, I had parentheses around these two. That's the only difference, right? So it says, okay, you want to add up the ratings. So I know that you are going to do that anyway. So I'm going to say, okay, let's add them up here. So it will be 9, and then I have 2 ones. So that will be 2. Or this guy has even more opportunity for combining. So you say, okay, 100, 100, 100, you're going to reduce by key at the end. So I'm going to add up all of these numbers, 11, add up all of these numbers, 3. Now you can see that the green data is less than the blue data, right? And now we shuffle the green data, which is less than
Yes.
that one, right? So
Sorry, Professor, I'm cutting. In the blue box above, right? So where you have 100, 102 and 1. Okay. So are we also summing? So when we're reducing by key, are we also doing it in parallel, or is it just done on a single core?
For a particular partition, it's a single core.
Okay.
Yeah. If you want more parallelism, you have to increase the number of partitions.
So but why can't we just do it in parallel for a single partition even? Is it slower?
So you have these on a list, right? So you want to do this in parallel. So 2 threads can go after 2 different keys. I think it's possible. But I think the point is that I think our operation is pretty fast on every partition. So we achieve parallelism basically by having multiple partitions already. But yes, you can increase the amount. That's true. I mean, for a particular node, worker node, you can increase the number of CPUs that you assign to it. Okay. And it can potentially take advantage of some local parallelism. Possible. Okay.
Okay. Thank you.
Yeah. And now, after you shuffle your data, we still need to perform the rest of reduce by key. We are not done, right? Because like 100 part of it is here, part of it here, and here. So we shuffle to one of the machines, for example, to the first machine, and then this first machine adds up these partial results again, right? And it produces something like this at the end, which is for every movie, sum of the values and number of reviews we have for that movie. Let's go back, see if it's done. Yes, exactly. Like movie 110 got, this is the sum of the reviews, and it got like 66,000 reviews, right? So we are almost done, right? All we need to this is to convert this thing to another key value pair. The key is fine. The value should be basically dividing these two numbers, right? So I can have something like result dot a map works, right? It's a one-to-one mapping. For every element we want to produce a new element, so it will lambda for every element give me a new key value pair. Just keep the first one, the key is just fine, no further operation required on the key. And for the value, right now I have a key value pair, just convert that into the average. So it will be something like this. So agree that x1 is referring to this key value pair, right? x0 is this, x1 is this, agree. And then this x1 itself is a key value in my implementation. So I can do this again, right? To access the first element or the second element, right? So x1, 0, it will be okay. x1 means go to the second element, which is this. And then here, give me the first one of this. So it will be this. This is sum. So if I divide that by same, and then this one, the second number, right? x11 will refer to the second number. That should be what we want. And because it's cached, I think it will be very fast now. There you go. So basically all I've done is that I took this number and divided it by this number and I replaced it here, right? That's what this map did. So it's 4 and so on and so forth. All right. And it was faster, right? The first one took this. I didn't watch it exactly. I think it says this take took 1 minute, right? I think I run the first approach on the real data, and it was after 5 minutes or even 10 minutes. It was not done yet, so I stopped. But this one was done in 1 minute, which was really good. And it is possible because of combining. So does the Spark have combiners? Yes, but they are not explicit combiners like Hadoop, where we say, hey, here's the combining method. No, by using proper operations, if you can, we can implicitly use combining, okay? Now, let's do another thing here. Instead of take 10, how about writing, how about storing the output? And before that, you got a question. I think this was covered last lecture. What did cache do? So cache, so this is an RDD, agree? And on that RDD, I applied an action, take 10. So at this point, it calculates this RDD. But after this line, there's no guarantee that Spark keeps this RDD in memory, meaning that the second time I'm accessing aggregate result RDD, it might be gone, meaning that it may need to go back to data, do all of these things, do the lengthy reduce by key again, right? But because I asked it to cache it, Spark does its best to keep it in memory, and obviously it was in memory, right? Because when the second time I ran it, it returned immediately, but the first time it took like a minute to finish. Does the calculation of aggregate result take place in line 17 and not in line 16? So it happens here, right? So the calculation, or better to say, remember, calculation, this is the definition. This is where we tell Spark that this is the definition of this RDD. This is how you can calculate this RDD, right? But we don't do it yet. We wait until we hit the first action. And here we see the first action. Now we go back and say, okay, you want to take the first 10 elements of this RDD? Okay, I know how to calculate it. The definition was here. So aggregate actually results RDD is calculated on line 17, this line. because of lazy evaluation, right? Talked about this last time. But here, when I say, okay, I want to do something with this RDD, it says, oh, I have it. I don't need to go back to line 16. It's already in memory. What do you want to do? I said, oh, I want to do the map. Oh, that's quick, right? I can do it for you very easily because it's in memory. All right, good questions. Okay, I wanted to add something. Instead of take 10, how about let's store this back to disk, right? We want all of this. Okay, looks fine. Now that I realize that it looks fine, I want to store it to a file. How can I do that? You can use save as text file operation. And then here you provide a name, okay? So let's call it rating. Let me cheat and see if I've already done that. No. So let's call it rating, okay? And the results will be stored in a directory with that name, okay? That's not the output file, that's the output directory. So let me run it again. Okay, done. And you can use the browser feature here. You can see that it created a new directory called rating for me, and it populated it with some results. Here, there are like 20 part files. What are these? Let's open them and see what we have here. So it looks like in the first one, yeah, it looks like we have the results. And then the second one, more results. Third one, more results. So what's going on here? Why did the Spark broke down the output into so many part files? There are 22 files here, starting from 0, right? 22 files here. Let me go back to my slides and explain something here. So the ReduceByKey, we created this, we took the average, right? Now we want to save to file. What happens is when you call save as text file, remember each RDD, including the final RDD that we calculated, has multiple partitions. The way it stores the RDD to disk when you call save as text file is that it basically locally stores that partition to that server. Okay, so this is server 1. It stores this partition. Server 2 stores this partition, right? But if it's a standalone program, right, which is the case in our setup here, it is one computer only, right? But it has multiple threads, so it simulates having different computers. So every partition is dumped independently to disk. That is why we end up with multiple part files. I ended up with 22 files. It suggests that my RDD had 22 partitions. That's why we ended up with 22 files. But in some cases, like our example, you will see that these part files are very small. If you look at these files, they are like some kilobytes only, right? So it totally makes sense to merge them into one file, right? But how can we do that? So if I can somehow get rid of this thing here, is it because the zoom is so bad? Is this why? Okay. All right. So one way to fix this issue is to reduce the number of, reduce is a bad word, right? Decrease the number of partitions. So at this time, this RDD that I'm saving contains 22 partitions, right? I want to make it one partition so that when I store it, it gives me only one file. And you can do that with a few different options, okay? One transformation that does this, less, and it accepts an input, which is basically the number of partitions that you want. I say 1. Just give me a new RDD that contains only one partition. And when I store it, that should give me only one part file, right? Because there's only one partition. Let's store that into rating 1. See what happens. Okay, it's done. Going back. Now I have a new directory, rating 1, and you can see there's only one part file in this file, right? In this directory, because I had only one partition. So what happened was that I didn't want 22 partitions, so I used coalesce to dump them to one partition. Okay, so that gives me a new RDD with one partition, and then when I save it, it gives me only one part file. Makes sense? There's another transformation that you can use called repartition. That one also accepts an input, which is the number of partitions that you want, and I let you search for the differences between coalesce and repartition. You may need to use them in your next assignments. There are also other topics that we cannot cover here. There are things like cache and persist. You can look up what is the difference. There are some more advanced topics such as broadcast variables and accumulators that you can also look up yourself. In the remaining time, I want to review and see if there's any questions before I move on. Okay, looks like there's no questions. Let me know. I want to finish the remaining slides that we had from before. Okay. So we talked about many of these things, but here let's make sure we cover. So there are some other key value operations, and there are many, many more, actually more than this, but these are some of them. You may need them for your assignment. Join. So if you have two RDDs, okay, you can join them. If you're familiar with databases and tables, you know that you can join two tables. It's similar to that, right? So if you have keys that they match, you can join those two RDDs. For example, here I have index 1, 2, 3, 4. This is another element here, and then I have the same thing with another element. So you can join them, meaning that you can create something that has this thing and then these two things, right, into one line. That's the join operation. It's similar to database join. We also have CoreGroup, which has a similar behavior. It just removes redundancy. For example, because index appears twice here, join will provide two lines with index, but CoreGroup basically combines them into one, right? It gets rid of repetition. So you can have a look at these, and you can create some RDDs yourself and play with these operations to see exactly how they work. Another important concept that I believe you guys don't use that much in your assignments is the level of parallelism. So basically, when you have aggregate by or group by key or aggregate by key or group by key, these kind of operations, it is not explicitly known how many worker nodes you should use to perform that operation, right? When you use things like map and filter, you know that, for example, you start with X partitions and you end up with X partitions, right? Because they have parallel operations. But when you perform group by key or reduce by key, we can have different number of partitions, right? Because if you have a full shuffle, usually the amount of data is less. We potentially can go to fewer number of partitions in some cases. We may need to go to more number of partitions, or in general, we can actually, Spark allows us to define how many servers should take care of that operation if it's like reduce by key or group by key. How can you specify that? We can specify that as the last parameter of those functions. So when you say reduce by key, and this is the definition like always, and then 5, it means that you should use 5 servers for performing this reduce by key operation. And because we are using 5 servers, we end up with an RDD that contains 5 partitions. Make sense? So basically, this is an, if you don't provide this number, Spark will pick something automatically, okay? Typically, it's the same number of partitions, so it keeps the number of partitions the same. But if you provide it, it will follow that. And again, it's only for operations such as reduce by key, where we have a shuffle. You cannot provide it for things like map and filter, right? And here is a high-level description of how your program is actually executed. Okay, Spark divides your program into multiple stages. These are basically these boxes that we draw here. Okay, so that it can come up with a plan to execute the code. All right. How can it find different stages? It has a very simple rule. You move forward, for example, here, you move forward until you have a shuffle. So here I have an RDD, okay? So this is an RDD. It has 4 partitions, okay? Sorry. It has 4 partitions. And I apply a map on it. That will give me another RDD with 4 partitions. You know about this. And then we have a filter, give me another partition. Sorry, RDD with 4 partitions, right? And there's no shuffle until now, right? It was pretty much locally done on the servers, and we know about that. But then you have a join operation. And here, it needs a shuffle. So that's the end of this stage. And then here, we have an RDD. And the first thing we do here after creating that RDD is a group by operation. And we know that it requires shuffle. So that would be the end of this stage. So basically, by looking at where we need a shuffle, it divides our program into stages, and it creates a graph. You can see that this is like a graph. It's called the DAG graph or DAG scheduler. The DAG stands for directed acyclic graph. It's directed because we know that the movement is from here to here, right? We have arrows, right? So it's a directed graph. And also it's acyclic. It doesn't have a loop in it, because if it has a loop, it never finishes, right? So that's about it. So it takes our program, creates a DAG from the program, and it runs it for you. In general, there are 2 types of operations: narrow dependency and wide dependency operations. Things like map and filter or union, they are narrow dependency because these are embarrassingly parallel, meaning that servers, individual worker nodes, can perform the operation locally without having to talk to other servers. These are narrow dependency, and they are fast operations. We have things like group by key, and you saw an example today. To complete these operations, we have to talk to other servers, and because of the shuffle that we need, it is pretty slow. Join operation is like that. It is a wide dependency. There is a special type of join that can be narrow dependency. It has some special requirements, but you guys don't need to worry about this, okay? It's too advanced, but know that some operations can be wide or narrow dependency depending on how we implement them, okay? Now, we started from 2 operations, right? When we taught Hadoop, when we learned Hadoop, we knew that, okay, we have a map, we have to define map, we have to define the reduce function, right? And then Hadoop takes care of everything. But we realized soon that this is a very restrictive API or instruction set. You would like to have some flexibility to have different types of operations, and the Spark provides a ton of those operations. I told you last time, and I emphasize again, whenever you want to do something, look it up to see if there might be an operation already defined that you can use. And in this course, you are free to use any operation defined on RDDs in a Spark, okay? So if you can use something, feel free to use it. That's the correct way of doing it, instead of re-implementing something yourself. So this was really a very brief introduction to Spark, okay? And you have learned pretty much most of the things you need for your assignments. There are cases that you need to look up the API, you need to make yourself familiar with some operations, right? We cannot teach you every single operation that Spark uses, but by doing some simple search, you can look them up, you can figure out what what they do, because now you know the fundamentals, so you can understand new operations yourself. Okay, and as we mentioned, this course is not about teaching these frameworks. We just taught you enough so that we can talk about algorithm design. And starting next week, we will focus on algorithm design only. I have a few more slides and then we wrap up this lecture. So the performance of the Spark is much better than Hadoop when we have iterative algorithms that need to repeat until they converge. Why Spark is better? Because the Spark keeps everything in memory, and when I perform one iteration, everything is already in memory. When I move on to the second iteration of the algorithm, the data is readily available. But in Hadoop, every time, at the end of every iteration, it stores stuff to disk, and then at the beginning of the next iteration, I have to read things from the disk, and this slows down the operation significantly. This is the performance of Hadoop versus Spark when running PageRank algorithm. I'm going to explain this algorithm later on. So you can see the y-axis is execution time, right? So lower is better. So we can see Spark beats Hadoop badly. And two other algorithms that you will learn in the machine learning and data mining sections later. Again, you can see the performance of Hadoop is awful compared to Spark. So Spark is really good for iterative algorithms because of this. I will go back to those performance charts when we learn about those algorithms, but I just wanted to give you an idea that Spark is really good for such algorithms. Now we want to talk about the ecosystems a little bit. So, and this is about how Hadoop and Spark coexist. Okay. We have a resource management idea called Yarn. Let me actually go to the second slide and go back to that in a second. So in the first iteration or the first version of Hadoop, which is the left side, we had nothing but Hadoop, right? This is many years ago, right? Because Hadoop was the first big data framework. So at that time, when people designed Hadoop, they had nothing in mind other than implementing Hadoop. So they implemented HDFS for file storage, and they implemented the MapReduce component, right? And the combination of these two can run any Hadoop jobs. Everything was fine. Soon, people designed some other frameworks beyond Hadoop, such as Spark. And people realize that, wait a second, if I have a company and I purchased like 1,000 servers and I built my own cluster, right? And I have Hadoop on it, everything is there. Now, if I want to use the Spark, does it mean that I have to buy another 1,000 servers and build another cluster? That's really inefficient, right? Can I just reuse my cluster of machines and I can use a Spark as well? And that's how version 2 was designed. It was designed in a way to accommodate other frameworks as well. So we have HDFS. HDFS didn't change. But now we have this layer in between, the resource management. This is the slide that I skipped. Yarn stands for yet another resource navigator. Not the best name, but I think the abbreviated form is nice. It's called Yarn. So it basically provides a general purpose framework so that you can run anything on top of it, including Hadoop, MapReduce, or Spark. Now, in the second version, it allows you to have a cluster of computers and you run Hadoop and Spark simultaneously. There's no problem with that. You can submit a Hadoop job and then you submit a Spark job. There's no problem. It runs. That's really beautiful. So that's the second version. So let me explain a little bit about version 1, version 2. In version 1, this is what we had when I talked about Hadoop early on in the term. I told you that there's like a master-slave architecture, right? There's a master node that takes care of everything. And this is what we have in this picture. So if I have a client, right, a red client, submits a job, it goes to the job tracker, right, which is the master node. And then this guy reserves some resources for you, for example, some for map and some for reduce, right? and then your program runs, right? And then another guy can come along, and this guy can also submit another Hadoop job, and that would be executed as well. It will have some map and reduce and done, right? So, but this framework only understands Hadoop. If somebody submits the Spark job, said, what are we talking about? What is the Spark? I don't understand the Spark. So in the second version, what they did, instead of here the master node for Hadoop, now they have a general purpose resource manager. Okay, and a bunch of working nodes, right? How does it work now? So we have a client, let's say this is a Hadoop client. How does this still work? No problem. It says, hey, I'm submitting this Hadoop job. It says, all right, no problem. I create an application master for you. The application master is like the previous master that we talked about, right? But instead of being a dedicated machine, now it's a dynamic module kind of thing that we load and we run for that job. Okay, so it has an application master. So the first thing that Yarn does, it creates application master for us, and then the application master looks at your application and says, okay, this is how much resources you need. Like before, it reserves some resources, and you can think of these things, these containers, as like virtual machines on the servers, right? And so it reserves some compute capacity for us on those machines, and then our map and reduce operations can happen inside those containers. And now, how does this new technique accommodate other frameworks? Now, this client, let's say it now submits a Spark job. Well, Yarn says there's no problem. I create the Spark application master for you. And then that master node will reserve some resources for you. In this case, apparently we didn't need that much, so we only reserved like one container, and everything happens. So this container is your worker node in Spark, right? You can have multiple. In this case, there's one of them, right? The container can run multiple nodes, right? This is resource virtualization, but you may need much more than that in practice for a big job. So this is the general picture for any system. So it can be Hadoop, it can be Spark, but this is basically the specific architecture or the downcasted version specifically for Spark. So you have your Spark, you have your driver program, right? Yeah, we have a Spark context, and this is how we basically run our Spark stuffs, right? Whenever we want to do anything in Spark, we start with sc.something, right? We create RDDs, and then we work with RDDs, and then we basically submit that to the cluster manager, which can be Yarn, and then that guy will basically create an application master and then we create some worker nodes, right? And then inside that worker nodes, each worker can take care of multiple tasks for us, right? So, and then we can basically, at the end, we can run an action and get back some results to the driver program. So this is the entire, basically, so it's the same architecture, but it's specifically for Spark. But the idea is the architecture is general purpose and accommodates different frameworks. And there are some other frameworks beyond the Spark that this architecture can support. And it's really beautiful, right? You have one set of machines, you install the Hadoop ecosystem, it runs everything for you. It's nice, it's really beautiful architecture. All right, that's it. Questions? I'm going to stop recording. Looks like there's no questions. So I will be around for a few more minutes.